in this video, I'm sharing with you a video that only 4 minutes video to see on how a membrane system works. So there are few types of membrane. There are few types of membrane. The first one is microfiltration. The second one is ultrafiltration. The third one is nanofiltration. The fourth one is reverse osmosis. The fifth one is electrodialysis. There are 5 types of membrane, and these are varies based on the pore size. These are varies based on the pore size. In other words, they are classified based on their pore size.
The St. Mary's Water Recycling Plant uses reverse osmosis to further treat wastewater after the ultrafiltration process. Reverse osmosis membranes are constructed from a membrane flat sheet. It is comprised of 3 layers: a polyester fabric support base, a microporous polysulfone layer, and a 0.2 micron thick polyamide barrier layer. The polysulfone layer strengthens the very thin barrier layer. It is the barrier layer that removes nutrients, chemicals, bacteria, and viruses from the water. The membrane flat sheet is combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets for the feed water. A sheet of permeate spacer is added to the membrane sheets and feed channel spacer. This enables the final recycled water product, or permeate, to flow evenly across the entire membrane surface, even under high pressure. The back of the membrane is completely sealed to the edges of the permeate spacer. The membrane sheets are glued along each of the 3 exposed sides and roll around the core tube. Feed water is forced through the feed channel spacer and into the barrier layer of the membrane. Water passes through the membrane surface into the permeate channel. It flows in a spiral direction and collects in the core tube. This water is the final recycled water product, or permeate. There are 7 spiral wound elements loaded in one pressure vessel. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced. Feed water is pumped at high pressure into the vessel. As it travels, small molecules like water pass through the membrane, while larger particles such as salt, bacteria, and viruses do not. The final recycled water product is collected from the end of the elements. The concentrate or reject from that vessel flows to another stage, producing more recycled water. At St. Mary's, there are 6 reverse osmosis treatment trains, each with 3 stages. This design produces the highest amount of recycled water with reduced concentrate waste. Stage 1 has 52 pressure vessels, Stage 2 has 24 pressure vessels, and Stage 3 has 12 pressure vessels. 58 million litres of feed water enters the reverse osmosis system on a daily basis. As the feed water passes through each stage, more recycled water is extracted. 65% of recycled water is extracted at Stage 1. The remaining 35% is passed through Stage 2, where a further 10% is extracted. The final 25%.
Okay, let me stop here for a while. This is known as feed water. What is feed water? Feed water means the untreated water or pre-treated water. So this is known as feed water, regardless water or wastewater. It can be untreated water, untreated wastewater, or pre-treated water or pre-treated wastewater. It's known as feed water, which is marked in green here. Okay, once it's being treated, it passes through the membrane pores. The one that can pass through the membrane pores is known as treated water. So in this case, it's marked in purple. Is known as permeate. Okay, so the one that cannot pass through the membrane pores, which is consists of the pollutant, is marked in orange here, and known as concentrate or retentive. Okay, so the one that cannot pass through the membrane pores during the first stage, will be considered as the feed water during the second stage. So this is the reason why that the numbers of the membrane elements has been reduced during the second stage and so on. Okay, I repeat. The feed water here, it can be the untreated water, untreated wastewater, pre-treated water or pre-treated wastewater. Why do I say pre-treated? Because most of the membrane system, especially reverse osmosis, is require pre-treatment. Without a pre-treatment, you have to treat the water. It cannot be simply raw water or raw wastewater. Why? Because the pores of the membrane are extremely small, very, very small. So since the pores are extremely small, for this reason, if you pump in the very raw water, it will the dirt will stick very quickly on the surface of the membrane, so thus it will clog the pores of the membrane. So that if we would, because using a membrane we do have a specific element that we would like to remove. That's why we have to apply a pre-treatment. The specific element that we would like to remove when we apply membrane is more on the very tiny, very small element, it's known like iron, molecule, ion molecules, for example like sodium, potassium. They are extremely small. So that this is why that we need to use membrane. For this reason, those suspended matter should has been removed before it being pumped into the membrane system. Okay. Okay, all right. So this is the feed water. Then the one in purple, is known as permeate. What is permeate? Permeate is the treated water or treated wastewater. Yeah. One mark in orange is known as concentrate, or retentate. What is concentrate and retentate? Concentrate and retentate is what is the impurities which cannot pass through the membrane pores. So that the impurities which is in water, in the form of water, will pass through the system and will become the feed water for the second stage of the treatment system. Yeah?
Is passed through stage 3, where the last 5% of recycled water is extracted. 80% of all feed water is recovered as recycled water. An average of 50 million litres of recycled water is produced every day at St Mary's.
Okay.
5% of
If you look at this carefully, during stage 1, 65%, they can recover about 65% of treated water. During stage 2, only 10%. Because the impurities is getting more concentrate. During stage 3, only 5%. Only 5% of the feed water they can recover as permeate or treated water. So in total, when we employ stages of the treatment, this will give us the total of 80%, 80% of water which can be recovered. 65 plus 10 plus 5.
recycled water is extracted. 80% of all feed water is recovered as recycled water. An average of 50 million litres of recycled water is produced every day at St Mary's. The remaining concentrate contains so much salt and impurities that to recycle it would not make economic sense. This concentrate stream of 8 million litres a day is sent to North Head Wastewater Treatment Plant, where it is treated and released into the ocean.
Okay, so the concentrate, the final concentrate, this one.
Litres of recycled water.
The remaining concentrate will be sent to water treatment plant. But in this country, most of the concentrate, from the membrane system will be sent for not really to a wastewater treatment. It will be sent directly into the ocean. Okay, so but the right way of doing is to send for the treatment in wastewater treatment plant, yeah, so that it can be treated, it can be released as a clean water. Nevertheless, it can be released as the treated wastewater. Nevertheless, uh, since we have a specific target, yeah, when we employ membrane, we do have a specific target for pollutant removal, yeah, so that the concentration of the pollutant in the remaining concentrate after the final stage of the treatment, it will be very high. Yeah, there will be extremely high concentration of pollutant. So special intention has to be given. Yeah, because the common domestic wastewater uh, cannot be used as the point of treatment. Yeah, due to the high concentration of sodium and calcium as well as magnesium. If calcium and magnesium are the pollutant of removal, yeah, pollutant that we would like to remove, yeah. But most of the time, reverse osmosis are being used, yeah, for the removal of minerals, yeah, for the removal of minerals, yeah, because the size of the minerals ion are extremely small, yeah, that's why we have to employ membrane. Okay.
Everyone working in or associated with the water treatment sector needs to keep well up to date. Our online course, Nanofiltration and Reverse Osmosis in Water Treatment, has been designed for working professionals who want to increase their knowledge of these technologies and their applications. Membrane filtration using reverse osmosis has universal applications, and an increasing number of water-related organizations are using it to ensure a supply of clean water for industrial use and drinking water. Learning about how these technologies work will enable you to better operate your own installations and make better decisions about investment and maintenance. In this 7-week course, you will engage in practical applications
I'm
to ensure a
interested with
supply of
this
clean
one. Huh?
water for
Okay.
these technologies.
You see, this is the reverse osmosis unit. Yeah, reverse osmosis unit, and there is one unit as a pre-treatment. In this system, they employ dissolved air flotation as well as the filtration, yeah, anthracite, sand, and there are filtration. So you can see, first coagulation process followed by dissolved air flotation as well as the filtration system. After this treatment process, there will be injection of the softener to soften the water, uh, and there will be another stage of the filtration because this is cartridge filter, and this is the RO unit. Reverse, whenever we employ membrane system, yeah, whether it's nanofiltration, microfiltration, or reverse osmosis, we have to use high pressure pump. Yeah, you know why? Because the pores are extremely small. Yeah, so if we cannot employ the high pressure pump, water cannot pass through the membrane pores, or it will take very long, yeah, for water to pass through the pores of the membrane, and that's why we have to employ high pressure pump. So this is considered as one of the disadvantages of employing the membrane apart from the high maintenance system, yeah, because of the usage of the energy, yeah, because we need to use high pressure pump, so that the longer that we use the membrane, yeah, the more cycle, yeah, of the treatment system, the more cycle of the treatment, the higher will be the pressure pump that we have to apply. Yeah, you know why? Because the impurities, yeah, will stick within the surface, yeah, that so that it will be the pore surface will be smaller, yeah, will become smaller, so that we have to apply higher pressure, the higher pressure pump. Yeah, so the longer that we we apply the system, we use the system so that we have to apply high pressure pump. On top of that, uh, in order to avoid inefficient usage of the energy, so we have to employ the chemical cleaning. Chemical cleaning. That's why I said when we employ this kind of system, it require scheduled maintenance and frequent maintenance too. Yeah. Alright. Let's see our final video on wastewater treatment. The membrane system for wastewater treatment. I'm looking for a membrane bioreactor. This one, maybe we can spend some time on this.
Membrane bioreactor, or MBR, is an efficient and cost-effective product for treating municipal and industrial wastewater. The system can produce a high-quality effluent that meets stringent discharge standards and is suitable for reuse. Membrane bioreactors can be customized and built to fit just about any site. This can require additional engineering and may add lead time for delivery and startup. The packaged membrane bioreactor from Coke Membrane Systems offers a convenient alternative to a customized MBR design. A package system consists of pre-engineered assemblies that can be rearranged in a variety of configurations to accommodate the restrictions imposed by floor space limitations. A typical package system consists of an anoxic tank and aeration tanks for biological treatment, an influence screen, a membrane module tank assembly, a filtration and chemical cleaning equipment assembly, and an air blower assembly. Most of these units are pre-plumbed and pre-wired at the factory to reduce installation time and cost. The installer simply connects the pre-assembled units in the field. The compact design of the package system has
Okay, so this is for wastewater treatment. For wastewater treatment, normally it's require more complex treatment before it can pass through the membrane system. It's require. Sometimes we have to even integrate the system where we use the conventional activated sludge system, and the treated effluent will pass through the membrane module.
It's a small footprint. The building block approach allows the equipment layout to be configured to fit buildings of various sizes and shapes. The system can be easily expanded by adding prefabricated assembly units to the existing treatment operation with minimal interruption. The first step of the treatment process is the mechanical screening of the incoming wastewater. The wastewater enters a screen that is equipped with a 2 to 3 millimeter perforated plate. The solid particles, or screenings, are retained and continuously removed from the screen unit for disposal. The screened wastewater flows into the anoxic tank. Within the anoxic tank, a submersible mixer blends the screened wastewater with the mixed liquor, returning from the membrane filtration tanks at predetermined recycle rates to achieve the desired level of denitrification. In the absence of dissolved oxygen, nitrate is converted to nitrogen gas in the tank. The wastewater flows from the anoxic tank to the aeration tank. Oxygen is supplied using air blowers and a diffused aeration system. A dissolved oxygen sensor monitors the selected range to help the operator maintain nitrification with the removal of organic material. In this oxygen-rich environment, organic material and ammonia and nitrogen are biologically oxidized to carbon dioxide, nitrate, and water. A pH sensor is provided in the aeration tank for continuous monitoring of the pH condition. From the aerobic tank, mixed liquor is pumped to the membrane filtration tank for liquid-solid separation. Puron membrane modules are fully submerged in the mixed liquor inside the membrane tank for direct outside to inside filtration. The membrane modules are made up of hollow fibers with a nominal pore size of 0.05 micron. These robust, reinforced second-generation hollow fibers are cast on an internal reinforcing braid to overcome the
So these are the cross section, and the cross section you can see, the one that can pass through the pores, so this is the wall of the membrane. So the one that can pass through the pores are the clean water. So the one that cannot pass through the pores are known as retentate or concentrate. And the clean water is known as permit.
For breakage problems typical of first-generation systems. The free-floating tips of the hollow fibers in the single-header design of the Puron module also reduce breakage by placing less mechanical stress on the fibers than in modules that use a double-header design. The membrane system is equipped with rotary lobe pumps that create suction inside the hollow fibers and draw water through the fiber wall to the permeate collection tank. A programmable logic controller, PLC, automatically controls the filtration and membrane cleaning operations, while a human-machine interface continuously monitors the system performance. The PLC is Ethernet capable to interact with other plant PLCs or SCADA systems. The rotary lobe pumps periodically reverse the flow at predetermined frequencies and durations to backflush the membrane fibers. Pneumatic valves, as well as pressure and flow measuring instruments provide continuous monitoring and control of system operation. When cleaning is required to restore the desired flux, a train of membrane modules is isolated from normal operation, and sodium hypochlorite and citric acid are sequentially injected into the membrane modules for in-situ chemical cleaning.
Okay, so this is where that we have to, this is what I mean by chemical cleaning. So in this case, they use a sodium hypochlorite for the chemical cleaning to remove the impurities which is stick on the surface of the membrane.
Excess biomass or sludge generated from the biological treatment process will be wasted on a periodic basis. To maintain the desired solids concentration within the system, sludge is withdrawn from the bioreactor tanks or membrane tank for proper offsite disposal by licensed haulers. Permeate generated from the membrane filtration process is transferred to a permeate collection tank. The high-quality permeate will meet strict local and EPA effluent discharge criteria. In many locations, the permeate is used for cooling tower water makeup, irrigation, and toilet flushing. In summary, the Puron MBR package system offers the following benefits: flexible layout configuration, factory assembled package, easily installed with minimal site preparation, low operating and maintenance cost, fully automated with remote data access.
This is too long. I will try to make the video about 7 minutes only.
$100 million per year. Puron,
This
a
is
young company based in Aachen, Germany. Puron was founded in 2001 by engineers associated with the University of Aachen, which is now
Ultrafiltration using hollow fiber membranes enables the clarification and disinfection of any type or quality of water.
So this one is nanofiltration, ultrafiltration using hollow fiber membranes. Okay, later, just now I did mention to you there are 5 class. There are 5 types of membrane, which is the first one is microfiltration, the second one is ultrafiltration, the third one is nanofiltration, the fourth one is reverse osmosis, and the last one is electrodialysis. And these are classified based on their pore size. However, membrane can also be arranged, or the configuration of the membrane can exist in different ways. One types of common configuration is known as hollow fibers. For this reason, hollow fibers membrane can exist in the pore size of ultrafiltration, Hollow fiber membrane, hollow fiber configuration can also exist in the pore size of ultrafiltration. It can also exist in the pore size of microfiltration, and it can also exist in the pore size of nanofiltration. Okay, so in the previous video, you have seen the reverse osmosis, and let's see today on the, let's see in this video on the ultrafiltration.
Several membrane elements. An element. Ultrafiltration using hollow fiber membranes enables the clarification and disinfection of any Ultrafiltration using hollow fiber membranes enables the clarification and disinfection of any type or quality of water in one single step. An ultrafiltration module is composed of a vessel and several membrane elements. An element contains thousands of hollow fibers, each with a diameter of less than 1 millimeter. The microporosity of the membranes allows for mechanical filtration of the water. Pore size is an effective barrier against suspended solids and microorganisms.
Okay, so when we employ ultrafiltration, we cannot remove the sodium ion, because the size of sodium ion is extremely small. For example, if we would like to treat, we would like to desalinate to conduct desalination of seawater to remove the salt, so that we cannot use ultrafiltration. You know why? Because the pores of ultrafiltration membrane is not really small, as compared to reverse osmosis. Just now when we employ reverse osmosis, it has the capability to remove the salt content. But employing this system, it can remove only the suspended solid as well as the microorganism, the bacteria in particular.
Bacteria and viruses. The high filtration capacity and sustained durability of the fiber is a result of the fouling-resistant hydrophilic polymers of which it is composed. Filtration is carried out in an outside-in, dead-end mode. Modules are thus compact and simple, with optimized filtration surfaces, without risk of fiber blockages. Backwashing with water and air allows for efficient, quick, and simple cleaning.
Okay, you can see backwashing
can be supplemented.
So it will it can remove the sticky material, the substance which cannot pass the membrane pores, which is known as retentate or concentrate.
With the addition of standard chemicals. The Giga membrane offers a choice of modules that are designed to match flow requirements and the quality of the water treated. Giga technology makes it possible to provide units with a wide range of capacities, which are also the most cost-effective solutions available on the market. The innovative Giga range of modules are compact and high-performing for use in a large variety of filtration applications.
Okay, that's all on video. Let me share my slide. Thank you for watching. Let's share my slide. Okay, great. So for presenting today, we have Torben, great. Then who's me? Number 2, number 3, Song. After Song, Jin Ching will be Mr. Hakim. Mr. Hakim already. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, great. Up to Nurul Ain. So we have 7 presenters today. Let me share my slide. Okay. We have 2 slides today. Okay. As I mentioned to you just now, we have about 5. The first one is microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and electrodialysis. The lower the position of these types of membrane, the smaller will be the pores. Yeah, I repeat, yeah. The lower the position of this membrane, the smaller will be the pores. Number one, number two, we don't have number one here. Number one, the size for number one is bigger than number two, the pore size, yeah. So number five, yeah, for the application of water and wastewater treatment, yeah, number one, number two, number three, number four, and number five, yeah, are what we use, yeah. Number one until number four are widely used for the application of water and wastewater treatment. Number five, yeah, are more familiar in the application for the development of artificial kidneys, yeah, electrodialysis, yeah, because the pores are extremely small, so it's not economical to be used for the treatment of water and wastewater, yeah. So at this moment, reverse osmosis is the best, the best membrane to be used for the treatment of water and wastewater. Okay, all right. So this is the classification of salt water. Yeah, even though the application of membrane is not mainly for the treatment of seawater, however, seawater are commonly being used to be treated, are commonly be treated using reverse osmosis. Yeah, so let's see, yeah, the glossary of salt water. The fresh water, if you are talking about fresh water, it should contain less than 1,000 total dissolved solid. Yeah, why in this case total dissolved solid are being used as the indicator for the salt water? Total dissolved solid, yeah, has a very strong correlation with salinity. Yeah, so if we measure total dissolved solid using TDS meter, it's like a pH meter, so that you can get the reading of salinity at the same time. Yeah, so total dissolved solid comprised of mineral ions. Yeah, most of them are sodium. Yeah, so for the fresh water, it should contain less than 1,000 milligram per liter. For brackish water, between 1,000 to 5,000.
Sorry, Doktor.
Any question?
Doktor present ke?
Tak ni Okay.
Ah,
Thank you, Isni.
okay.
Okay. Okay. Yesterday also I lecture with master student and today with the bachelor student. Okay. Thank you, Isni. Okay. All right. I have to repeat again. We have five system. So the lower the position of this membrane, so the smaller will be the pore size. Yeah. So number one until number four, these are the most common membrane types that being used for the treatment of water and wastewater, while number five are not very common for the treatment of water and wastewater, but still under development, for the artificial kidneys. Apa kidneys, buah pinggang. Okay, so glossary of the salt water, if we can classify based on the concentration of total dissolved solid, less than 1,000 milligram per liter is considered as fresh water. Brackish water 1,000 till 5,000. Highly brackish is 5,000 to 15,000. And saline is about 15 to 30,000. The seawater normally consists of the concentration of total dissolved solid is about 30,000 to 40,000. Yeah. So normally the concentrate from the membrane system, the concentration of the TDS is about 15 to 30,000. Okay, it's considered as saline water. Yeah. Okay, what's a membrane? Yeah. It is a thin barriers or films of material that allow certain substances to pass through. Yeah. Membrane are made of polymers. Yeah, our bodies have numerous semi-permeable membranes that allow nutrient in and toxin out. Yeah, so is a semi-permeable membrane because it allows some substance to pass through. So we have about 5 types of membrane, and we are interested to remove the small particles, molecules, and ion in solution. So as I mentioned just now during video presentation, if you are interested to remove the suspended solid, so that we don't have to apply membrane, because application of membrane, when we apply membrane, meaning to say that we do have a specific pollutant to be removed. If we are only dealing with the if the raw water contain of suspended solid, we don't have to apply membrane, because it's not very economical. We can apply coagulation and flocculation instead. Yeah. So this is where, this is at your level. Later towards the end of this course, you should be able to determine, you should be able to evaluate, and you should be able to recommend what is the correct technology to be used, based on the scenarios. For example, if you are dealing with oil and grease, is it membrane suitable to be used for the removal of oil and grease? Definitely not. If you are dealing with high concentration of suspended solid, is it membrane are the best technology to be used without any pre-treatment? Definitely not. Unless you are looking for the removal for tiny ion, tiny particles, dissolved minerals, then only membrane is suitable to be used. Okay. Okay. This how do we classify? If we can imagine, if I can tell you the size, the pore size of the membrane. Okay, water, the size for water is about 0. Water molecules. The size for water molecules is 0.002 microns. So these are the reverse osmosis. Okay, so sodium ion, the size is about 0.0037. That's why I said sodium ion cannot pass through the reverse osmosis. The size for the hemoglobin is about 0.007. It's bigger than sodium ions. So it can pass through the nanofiltration. And the viruses, the size is only 0.1, not too small as compared to sodium ion. That's why I say, if you are looking for the removal of viruses, if you are looking for the removal of bacteria, application of microfiltration and ultrafiltration probably is sufficient. Are sufficient for the removal of bacteria as well as viruses. Why? Because the bacteria, the size is about 1 micron. Even microfiltration can work well for the removal of bacteria. Okay, so this is how do we see the size, if you can imagine, the pore size of each of these types of membrane. So microfiltration range between 1 to 0.1. Ultrafiltration range between 0.1 to 0.01. Nanofiltration, the range is range between 0.01 to 0.001, while the reverse osmosis is range between 0.001 to 0.0001. So anything larger than this size, it cannot pass through the modules. Okay, so these are the configuration of the module. So this one is the reverse osmosis module for reclamation of secondary treated water in Kranji New Water Plant, Singapore, and this one in the United States, reverse osmosis. Most of the system they employ hollow fiber configuration. Hollow fiber configuration is and normally reverse osmosis are being used as a final barrier, because it can remove the dissolved mineral very well, demineralization, removal of ionic constituent, and pressurized vessel with a spiral spiral membrane. Yeah, so whenever we employ a membrane, we have to apply the pressure pump. Otherwise, it cannot pass through the membrane modules. Okay. 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 Next one. Okay, wastewater reclamation. Advancement in membrane technology in the last 2 decades, and mass production has made wastewater reclamation as a feasible, as feasible for a large scale application. For this reason, two main membrane process are normally being used for wastewater reclamation, which is microfiltration or ultrafiltration, as well as the reverse osmosis. Okay, normally microfiltration and ultrafiltration are being used as a pre-treatment system for reverse osmosis. Why? Because since the pores are extremely small, so having microfiltration or ultrafiltration as a pre-treatment module can delay the formation of the cakes. What do I mean by cakes? Formation of clogging material within the pores of the membrane surface. So that if we would like to expand the period for before we have to conduct the maintenance. So the pre-treatment module has also the pre-treatment system can be we can use a microfiltration or ultrafiltration. It's not necessarily to employ a coagulation or common filtration system. Using two sets of membrane. Sometimes it can reduce the potential for the cakes formation, which cause clogging of the membrane pores. So these are the classification. These are the characteristics of the membrane of the microfiltration and ultrafiltration. The size are between 0.001 to 1 micron. It can remove particles, colloids, microorganisms, used as pre-treatment of secondary effluent before it can pass through the reverse osmosis, and it can prolong the cleaning interval. This is what I mean. We can prolong the period before we have to conduct the chemical cleaning. Before we have to conduct the maintenance work. For the reverse osmosis, the size is extremely small, about 0.0001 to 0.001 micron, which can remove more than 90% of sodium chloride as a final barrier for wastewater reclamation, and is the major application. Yes, RO is the major application in desalination for brackish water, for ultra pure water. In our lab, we do have one machine, ultra pure water machine. So this is this system they employ reverse osmosis. So pre-treatment is a must for reclamation, because we would like to delay the period before we conduct the chemical cleaning. In some treatment system, they did not employ the MF or UF. They employ common conventional system like coagulation, flocculation, and common filtration system. Okay, later we have to calculate the not today, because we have another 2 weeks to complete on this topic. As this is a very long topic, very long topic with a lot of design calculation. Okay. All right. So later we are going to calculate what do we call as silt density index. Knowing the silt density index will tell us the degree of fouling. Foulings mean the clogging within the pores of the membrane is known as fouling. So that when we know knowing the value of silt density index, that will tell us the degree of foulings, and that will also tell us whether the pre-treatment is required or not. Okay. These are the commercial membrane configuration. These are the hollow fibers. Yeah, we do have hollow fibers, we do have tubular membrane, we do have flat sheet membrane. These are all configuration. Yeah, and microfiltration membrane normally being used as a pre-treatment to reverse osmosis. Yeah, we have two types: pressurized and submerged. Yeah, some of the membrane module are submerged. Yeah, are submerged within the water tank or wastewater tank. Some of them exist as a separate system. Yeah, so these are the historical development of the membrane. I think they have come up with innovation on the membrane technology. In couple, they have embedded the technology with titanium oxide, yeah, to have a better removal for a specific pollutant. Yeah, so there are so many innovation, yeah, on this technology. Yeah, so these are the table number 2 is a comparison, yeah, between the membrane structures. Yeah, so as I mentioned to you just now, the smaller the position of these membrane types, the smaller the lower the position, the smaller will be the pore size. Yeah, I have one let me share with you first. Yeah, okay, this one. I'll close. Okay. Dia berat. Saya buka dekat Adobe. Okay. Okay, so these are the comparison, yeah, between the membrane module. Okay, hope you can see. Yeah, so the first one is microfiltration. Membrane driving force is the hydrostatic pressure. Yeah, so typical separation mechanism is using sieve mechanism. The size, operating range, and these are the constitute that can be removed: total suspended solid, turbidity, protozoa, cysts, and some bacteria and viruses. Not all. If you employ microfiltration, not all. Only some of the bacteria and viruses can be removed. Yeah, if we go down to ultrafiltration, it can remove macromolecules, colloids, most of the bacteria and viruses, including protein. Okay, so nanofiltration, it can remove small molecule, most of the viruses and the hardness. What is hardness? Hardness means it can remove the magnesium, yeah, and calcium. Yeah, hardness is due to magnesium and calcium. Yeah. So you can imagine here how small the size of the magnesium and calcium molecules. Yeah. So applying nanofiltration, we can remove the hardness of the water. Yeah. Why do we concern about hardness? Yeah. Hardness can cause high consumption of soap. Yeah. So is the higher the concentration of hardness in water, it will lead to high soap consumption. Yeah, okay, that's why in water treatment, we have to soften the water by through addition of lime, yeah, to reduce the hardness. Okay, reverse osmosis, yeah, very small molecules. It can remove color, it can remove hardness, sulfates, nitrates, sodium, and other ion. Yeah, and the last one is electrolysis. It can remove colloids, most of the bacteria, some protein, and some viruses and protein. Yeah, dialysis and electrolysis, and it can remove ionized salt ion. Yeah, but these two systems are not very familiar. Yeah, are not familiar in the treatment of water and wastewater. So we are focusing more on the MF, UF, NF, RO, and RO only. Okay. Let's continue our lectures now. Okay. Okay, this is how these figures show you how the system works. Yeah, there are two configuration in terms of how does water pass through the membrane module. In the cross flow configuration, a percentage of the concentrate, yeah, percentage of the concentrate. Because what is concentrate? Yeah, concentrate means water that cannot pass through the surface of the membrane. Yeah, so in concentrate normally consists of the impurities. Yeah, that's why it cannot pass through the membrane module. Yeah, so the feed water, the concentrate cannot pass through, and you can collect the permit. Yeah, permit meaning to say that the treated water or treated wastewater. Yeah, so these are the cross flow configuration. Yeah, so in a direct filtration, dead end filtration, there is no recirculation. So these are the difference between the first and the second figure. Okay, the first figure is exactly in the first video that we watched just now. Yeah, because the concentrate are being recycled as the feed water. Regardless they are recycled, regardless they are recycled into the following module, or they can also be recycled into the same module of membrane. Yeah, if you still remember in our first video, the concentrate will be flow as the feed water for the second stage of the membrane module. But in this case, yeah, the concentrate are flow into the same membrane module, meaning to say that they have only one stage of membrane, but they recycle. Yeah, they recycle the concentrate until it cannot pass through the membrane surface anymore. Yeah, as compared to the second diagram, these are the dead end system where there is no recirculation. Yeah, so this system work based on 100% recovery of the feed water. Yeah, so in this system, there is also concentrate that being produced, but there is no recycling. Yeah, there is no recycling or recirculation. Okay, these are among the parameters that we have to monitor when we employ membrane system. Yeah, which is known as transmembrane pressure (TMP). Yeah, these are the pressure which is used to drive water through the membrane. Okay, transmembrane pressure are the pressure that being used to drive water through the membrane. Okay, so P1, yeah, pressure at the inlet of the membrane module. P0 is the pressure at the outlet of the membrane module. Uh, PP is the permit pressure. Okay, next flux. Flux are the, if this one, TMP, transmembrane pressure is something that we can control. Yeah, the pressure of the water. Yeah, we can force. Yeah, we can determine which pressure level that we would like to apply as long as the water can pass through the membrane module. Nevertheless, if we are talking about permit flux, yeah, these are the indicators. Yeah, these are the indicators. Why? What is flux? Yeah, flux is ratio of permit flow rate to the membrane surface area, and this is expressed in unit of liter per meter squared per hour. Okay, so in other words, yeah, as a layman definition, flux can be defined as amount of water, which is the amount of water which can pass through the membrane media, yeah, for a certain size of the membrane media for a certain unit of time. Yeah, so flux is the indicator whether the system works well or not. Yeah? Okay, sorry for the interruption. All right, so flux are the indicator to tell us, yeah, you know, during the first pumping, yeah, let's say you imagine you have one membrane module. During the first pumping of your feed water, you can collect about 200 meter cube. Yeah, but after second cycle, the volume of water which can be collected keep reducing. Yeah, so this the we can express this as a flux. Yeah, the flux value, the flux level. Yeah, why the volume of water keep reducing? Because of the fouling development. Yeah, the pores started to clog. Yeah, so a major design factor used to determine the numbers of memory units required for a specific plant capacity. Yeah. Okay, so we will be going through the calculation on the flux as well. Yeah. Okay, so permanent flux is design engineer will try to reduce the overall capital cost of the membrane system through implementation of higher membrane flux. Yeah? However, operating at higher design flux will inevitably increase the operating cost due to higher operating pressure, more frequent cleaning, and potential membrane replacement costs. Okay, so what do we do? In order to increase, yeah, in order to increase the flux, yeah, we have to apply larger surface area of the membrane. Yeah, so this is why it will lead to higher operating costs, and we have to conduct frequent cleaning. Why we have to conduct frequent cleaning? Because if we can go back to the unit, yeah, of the flux, yeah, it can be expressed as the volume of water which can be treated, yeah, to the area of the membrane per unit of time. That's why, yeah, the design engineers, yeah, if will try to reduce overall capital cost, yeah, capital cost of the membrane system by so that we can increase the volume of the permit produced, the volume of the treated water which can be produced. Nevertheless, employing this system should have some disadvantage, yeah, including higher operational costs, yeah, higher due to frequent cleaning required, yeah, and we have to sometimes when you force, yeah, too much of water to be treated, you end up you end up you need to replace, yeah, the memory module itself. Yeah. Okay, recovery. What is recovery? Yeah? Ratio of permit flow to the feed water. Okay, permit flow mean the treated water or treated wastewater. Feed water is the untreated water or untreated wastewater. Yeah. So the final one, oh, okay, I missed another one. Actually, there is another one which is known as rejection. Yeah, rejection rate. Yeah, okay, let me update now, otherwise I will forget. Okay, okay, this is the example. Let me add now. We have another one which is known as a rejection. Yeah, rejection. Okay, what is rejection? Yeah, rejection ni dia sama je. Yeah, rejection is equal to removal. Yeah, rejection is equal to removal and normally being expressed unit of percent. Yeah, so the rejection rate. Yeah, so what is the difference between rejection and what ni? Stimulation. Okay, so what is the difference between rejection and recovery? Yeah, recovery is the ratio of the permit, yeah, the ratio of the treated water or treated wastewater to the to the flow rate of the is the ratio of flow rate of the permit water, how much water can be produced after the treatment to the feed water, yeah, to the untreated water or wastewater. While the rejection is the removal. Yeah, how do we calculate the removal? Yeah, for example, if the TDS, total dissolved solid in feed water, is equal to 100 milligram per liter, so and TDS, yeah, TDS in permit, yeah, permit means to say that the treated water or wastewater only 10 milligram per liter. So how do we calculate the rejection? Yeah, so the rejection is equal to 100 minus 1 minus 10 divided by minus 10 divided by 100 and times. Can someone calculate for me this? 100 bahagi tolak dengan 10 bagi 100. 100 minus 10 divided by 100. 100 is percent, ya. Apa? 90 ya?
0.9.
Berapa?
0.9.
Salah. Sorry tak, bukan saja betul. Saya yang salah. Okay, okay, this one and times with 100%. Okay, 100 here is the feed water, minus 10 is the concentration of the TDS in permit water. After the treatment, the concentration of TDS become 10. So divided by 100, 100 is the original concentration of TDS in feed water times 100. I think I should use another value lah. Too confusing. Yeah? Okay, so can someone help me to calculate this? Okay, divided by 200. So 100 here is to get the percentage lah. So what is the value?
90.
90%. All right, thank you very much. Okay, so the rejection rate is equal to 90%. Yeah. So calculating the rejection rate in membrane system is exactly how do we calculate the removal rate in other treatment system. Yeah, but in membrane technology, they don't call removal, they call rejection. Right? Okay, following that, okay, these are what I have been trying to tell you all this while. We have a membrane module, regardless we use any types of the membrane system. We have feed water, which is the untreated or pre-treated water, and it will produce the permit, which is the product water or treated water. At the same time, the one that cannot pass through the membrane module is known as retentate or concentrate. What is retentate or concentrate? It's waste or pollutant which cannot pass through the membrane pores. Okay, so these are the entire diagram. So if you are talking about QA, let's say if we replace this with QA, we replace this with QC, we replace this, this one is represented by QB. So we can actually make one equation. Which is QA equal to QB plus QC. Okay. Any question? Okay, they should work as a balanced system. That's why I make this equation, because QA, anything comes in, it should come out, whether it will come out as a permit or it will come out as a retentate. Okay, that's why QA equal to QB plus QC. Okay, so let's try. We have two examples here before we can start with your presentation. Okay, maybe all of you can work with example number 1. Determine the rejection rate for a groundwater sample which is treated using a membrane system ultrafiltration. given to you the total dissolved solid in feed water is equal to 1200, the total dissolved solid in permit is equal to 200. Okay, you can try now. You can spend only 3 minutes now to calculate this. Okay. Okay. So 1200 minus 200 divided by 1200 times 100. So what is your answer? What is the rejection rate in percentage?
83.3.
Yes, correct. Thank you. Yeah. Anyone having difficulties to get 83.3? Yeah. So 1200 minus 200 divided by 1200 times 100. Yeah, you should be able to get 83.3. Okay, second example. Determine the rejection rate. By the way, anyone having difficulties to get example number 1 to get 83.3? Okay, should be okay. Alright. So example 2,
No,
determine
I
the
get
rejection
the same
rate.
answer.
Okay, great. Determine the rejection rate for a groundwater sample which is treated using ultrafiltration system. Given to you the TDS in feed water is 2000 and the retentate, this time around you are given the retentate is 1400. Okay, in the previous question you are given the permit. Okay, now you are given the retentate. Okay, you can calculate now.
We get 30%, 70%.
70%, correct. Okay, so how to do this? Yeah, maybe some of you having difficulties. Yeah, if we can go back to our previous slide. Yeah, what is a retentate? Yeah, retentate are the waste, yeah, which can pass through the membrane pores. Yeah, so if you are given the value of permit, you can simply minus QA minus QC over QA times 100. But in this case, you are given the value of QB. Yeah, so that you need to QA minus QB, yeah, then only you will get the QC. Then you have then QA minus QC divided by QA. So in this case, yeah, you have to 2,000 minus 1,400, so that you will get berapa? 600 kan? 600 is the 600 milligram per liter is is equal to the permit. Okay, then only from here you can calculate the rejection rate is equal to 2,000 minus 600, sorry, divide by 2,000. 2,000 and times 100. Okay, times 100%, then you should get around 70% rejection. Okay, any question regarding on example 2? Okay, bear in mind because this time around you are not given the value of permit. You are given the value of retentate. So that's why you have to find the value of permit first, then only you can proceed with the calculation. Okay, I think that's all for today, our lecture. Maybe maybe we can start with the presentation. Okay, I will stop presenting. Maybe Torben can start sharing your slide. Torben?
Yes,
Okay, you can start sharing your slide.
just give me a second.
Sorry, any question?
No question. I just need a second.
Okay, you can share your slide.
Okay. Can you see everything? Yes, perfect. Okay, then I just start. Selamat tengah hari, everybody. Good afternoon.
Selamat tengah hari.
I will give you a short overview about wastewater, the current wastewater situation in Malaysia. The current scenario, there are different types of wastewater. They are categorized in domestic. The daily wastewater use or production of one person is in average 225 liters each person. Then there's industrial wastewater. In modern industrial companies use on-site wastewater treatment for the treatment of their wastewater, because the wastewater is highly contaminated. Then there's agricultural wastewater, which is also highly contaminated by pesticides and nitrate. And then there's wastewater by public institutions like schools and hospitals, which is differently contaminated. For example, hospitals have highly contaminated wastewater, which needs special treatment. And at the end, there's stormwater runoff, which is collected in Malaysia in a separate sewer, and that's called the stormwater sewer. Malaysia also deals with the population growth, which leads to increasing amount of domestic wastewater. And in heavy rain periods, Malaysia needs to deal with large stormwater amounts, what tackles their stormwater sewers. To the current technology in wastewater treatment plants is divided in 4 different stages. There's a preliminary treatment. In preliminary treatment, such as in primary treatment, they use physical methods for the removal of contaminants. In the secondary treatment, which is also called biologic treatment. They use organic compounds. They want to reduce organic compounds through biological cultivation with a controlled population of bacteria. And in the tertiary treatment, which is an additional treatment, they use biological, chemical, or physical processes to remove pollutants like nutrients, metals, or organic chemicals. After the treatment processes, the effluent gets disinfected to reduce the disease-causing microorganisms that still remain in the current effluent. They mostly used for disinfection is chlorine, but in modern wastewater treatment plants, they use ozone or UV. And at the end, if they used chlorine for the disinfection, there is sometimes a dechlorination that avoids chlorine access to the environment. So what are the current problems Malaysia is dealing with? Malaysia has still a significant amount of wastewater which is still directly led into the sea and river. In heavy rain periods, the sewer system could exceed its load limit, and the wastewater treatment plants could get overloaded. Furthermore, solid waste leads to blocked sewers, and there's an increasing amount of microcontaminants like microplastic or antibiotics. The future technology and concepts are, for example, the use of high-quality membrane filters, like we just heard in the lecture of today. They can be used ultra membrane filtration or nanofiltration for a quaternary treatment stage in the treatment process, or they can be used active carbon filtration. Then there's definitely an urgent need of a development of the wastewater infrastructure of the sewage system, that there's less or no water that is directly led into the river without any treatment. Furthermore, regarding rainwater, Malaysia should aim on-site rainwater infiltration to relieve water treatment plants. But for this solution, it's a multidisciplinary task. So there are other kinds like waste management that also have some responsibilities in that issue. And public awareness should be raised by public information campaigns. Here you can see the additional quaternary treatment in the water treatment process, where microplastic and antibiotics could get removed before the water gets into the river or the sea. That's it. Thank you very much.
All right, thank you very much, Torben, for the good presentation. All right, so if I can ask one question regarding on the technology that being applied in Germany. So for the quaternary treatment, to what extent that in Germany the system has been used for the quaternary treatment?
In quaternary treatment, Germany is still in the survey process. So they have some they have some water treatment plants where they try that kind of system, and they research about the efficiency. But it's not common that there is a quaternary stage. They are just in the evolutionary process right now.
Okay, so it can be exist as a separate treatment for a specific industries, yeah? Am I right?
Yes.
Okay, because maybe the macro pollutants might not exist in a common wastewater, especially domestic wastewater, but maybe specific industries do produce the microplastic, for example, in their treated wastewater, which require quaternary treatment as presented by Tobin just now. All right, thank you very much, Tobin, for sharing with us the information. All right,
Yeah,
so
thank you too.
next, okay, welcome. So I would like to invite maybe siapa ya? Aina ya? Siapa tadi? Husni dulu, Husni Hakim. Husni, you can share your slide. Thank you.
Alright, okay. You guys can see my slide.
Yes.
Yes, we can. You can start your presentation now. Thank you.
Hello and Assalamualaikum to everyone. So my name is Muhammad Usni Hakim. My matrix number is 198517. So today I'm going to present about the wastewater issue in Malaysia. So basically, water quality, we can get a good water quality. So basically, there are three major pollutants that exist in our water, which is biological oxidation, ammonia nitrogen, and suspended solid. This is because the water is untreated or improperly treated sewage. So the most common types of wastewater treatment in Malaysia, according to the Indo Consortium, put some cage inside at the outlet where we trap the rat, trash, sand, all, and grease removal. So at the primary, we are going to settle the solid and the floating are being removed. So the secondary treatment and the solid. So these are the flowing constraints uh, in wastewater treatment. So the first one, under the current situation, low sewage price cannot cover high operating and maintenance costs. That means that the government give the tarif for uh, wastewater treatment is low, so it's quite low. So in order to operate and maintain the wastewater in Malaysia, it's quite hard. So the second one, the sewage industry dynamics, in which private developers build sewage infrastructure and then it transfer it over to public operators. It will create factor for poor quality which affect treatment procedure and operation. Which means the private sectors, they build the wastewater treatment plant and then transfer it for how to operate the system well, and suddenly can cause some effect to the water treatment. The third one is collection of several service by operator is not conducive. The fourth one, moderate and moderate non-compliance or non-compliance of some industrial, commercial and food business premises that do not have grease trap or do not maintain grease trap adequately has resulted in high oil and grease influence being released into the STP. So some industrial or food business, they don't have the grease trap before they discharge their oil, their wastewater to the drain. And the fifth one, among the other factor contributing among the other factor, which is the disposal of excess soap, detergent, and other cleaning agents into the sewer system. So these are some example which is the palm oil industry in Malaysia. So according to the report by the MPOC 2012, Malaysia is one of the world top producer and export of palm oil with 39% of global production and 44% of global export. However, this production of palm oil has produced oil pump due to its high production volume and it's complicated to treatment. So on the right figure, it shows that the pomade is produced in the palm oil process that consists of sterilizer, condensate 50 to 60%, separator sludge 60%, and hydrochlorine 4%. So the color of the effluent is yellow. It's odor. The effluent is non-toxic, but it has high amount of uh, nitrogen, phosphorus, potassium, magnesium, and calcium. So pomade consists of 95 to 96% of water, 0.6 to 0.7 of oil, and 4 to 5 of total solid. So operant register and extended aeration system or closed anaerobic register and land application system. Here are the flow of the pomade treatment process. As we can see, the first step, they do the oil trap, they trap the oil, and then the discharge been transferred to the cooling point, and the point. And last one, they go to the algae point and finally be discharged. So here are the standard palm oil mill effluent. According to the DOE, we have the oil discharge limit and the Environmental Quality Act. So before they discharge the palm oil effluent, they need to follow the standard. So impact to the environment. So without being treated the palm oil effluent, it will cause the water pollution due to the high nutrient content of uh, nitrogen, phosphorus, potassium, magnesium, and calcium. It will lead to plant growth in the aquatic region. Pomade also with pomade in water body could lead to the water source for the resident in rural area. Pomade also will contribute to the greenhouse gases, methane or biogas generated during the anaerobic digestion of pomade. Next, so the technology for problem solving. So basically they develop a system where zero discharge of palm oil waste. This system was generated by introduced by the Genting Jambongan, and the first idea was been established in Sabah, Malaysia. So the incorporation of the compost plant that converts all the mill waste and byproduct into the biofertilizer. The system is capable of evaporating all oil mill effluent and removing the requirement for the effluent treatment and soil irrigation. The biofertilizer produced is extremely nutritive and can be applied to farm field as replacement for at least 80% of the inorganic fertilizer that should be used. That's all for me.
Alright, thank you very much, Husni Hakim. So what is the tertiary treatment that being used since they recycle the treated wastewater?
Sorry?
What is the tertiary treatment that they use? Ultrafiltration, because I cannot see clearly here. What is the tertiary treatment?
For the tertiary treatment,
Uh-huh. Can you go to the final slide just now? Slide number 6.
this one.
Yes, they use ultrafiltration.
Mm.
UF as the final treatment, so that they produce a zero discharge. Yeah? Where is this system, Husni? Where they apply this
Uh,
system?
Based on my reading, the system is in Sabah, in
Oh, in
Zamboanga
Sabah.
Oil Mill.
I see. Alright. Thank you very much, Husni, for your good presentation. Alright, next can we have our friend here, maybe So Jincheng? So Song Jincheng.